Hey there, guys. We're going to be live streaming someone that's going to do a talk from about James Webb. And as soon as they open their end, we will be officially live. So get ready for it. And I've scheduled out that every weekend, starting in July, the 5th and 6th, I will be doing live streams every weekend. As many as I can, weather permitting and time permitting, everything of life permitting. So we'll be live streaming that. Now I'm going to switch myself off. Moment, guys.
Today we have a really exciting topic. We're going to be talking about a brand new kind of galaxy that has only been discovered in the last few years by the James Webb Space Telescope, called creatively enough, little red dots. And of course, he's a huge advocate for science outreach and education. And interestingly enough, he is a painter who is quite accomplished and does watercolors of pets on commission. So if you have a strong desire to have your pet painted, you can ask for his rates. Just as a reminder, this was the public lecture series hosted by Dr. Frank Summers, and we have now rebranded to Deep Space Dialogues. So please remember to subscribe to the Space Telescope Vision channel for all future videos that we have. And here you will also see visualizations that come out of our team, things like exploring the cosmic cliffs in 3D. So you'll be able to see all of those things when they come out instead of having to wait. So with that, we can go ahead and get started here with this dialogue, and I'll stop sharing and want to, I guess, get started, Kevin, with just asking what the deepest look we had at galaxies was before Webb launch. What's the situation look like before Webb comes on the scene?
Yeah, so if you want to put my slides up on the stage,
Absolutely,
we can. Yeah, great. So thank you first off for having me. This is really exciting. I'm really there's so many cool things to talk about with JWST, and if you were excited about this, folks who are watching, this is such a wonderful, beautiful little corner of what is an enormous football field size space for discovery that we have with this, and you're going to hopefully get some sense of our excitement over the course of this. But JWST revolutionized all of the field of extragalactic astronomy, but we have to pay our respects to the fact that there was a lot of work that was done by Hubble before JWST, along with some other telescopes we'll talk about. And before JWST launched, there were a couple very famous images. Among many of these images, these types of images, but probably the most famous were these two, which people watching at home might be familiar with, the Hubble Deep Field and then the Hubble Ultra Deep Field. The Hubble Deep Field is 1995, and it was essentially based on director's discretionary time. Let's just point Hubble at a region of the sky that should be free of stars, open the shutter, and just see what we get. And it turns out that we get galaxies. The whole universe is chock full of galaxies. And it's kind of beautiful because this is, such a tiny, tiny little patch of sky. And there's, hundreds and hundreds of galaxies in this, hundreds of galaxies across this whole field. And about 9 years later, in 2004, we took another region in the southern hemisphere and did a very similar thing with Hubble, the Hubble Ultra Deep Field, which looked even farther back in terms of the fact that it was getting a more deeper view of the universe. And really what we learned from all this is that every single place you point, there is galaxies. And what's cool about this is that every one of these galaxies, with these Hubble data and with ancillary data taken with other telescopes, we can really understand what's going on. How big are they? How many stars do they have? Are they making stars right now? Why are they those colors? Why are they those shapes? And when you are a child, like I was in the 90s and into the 2000s, I was, 10 when the Hubble Deep Field North came out, and then 19 when the Hubble Ultra Deep Field, this is revolutionary. These changed my life. Seeing these in books and newspapers, if this is one tiny chunk of the sky, what is the whole sky like? And I didn't realize at the time looking at this, but I, because of the fact that I work on a team that has looked at this, and we're going to talk about it later, with JWST, I'm intimately familiar with almost every galaxy in this. I know these galaxies so well. I was at Harvard a couple of weeks ago sitting in the office of Dr. Daniel Eisenstein, and he had a picture from the Hubble, a zoom in on the Hubble Ultra Deep Field. And he was like, I can't figure out where it is. And within seconds, I was like, oh, it's right here. This is where it is in the Hubble. I've just looked at this, close my eyes, I see galaxies. But this was the deepest, and it really showed us light that had taken, that was very, very faint, that was from very far away, because the universe is expanding and it takes light time to get to us. We're actually seeing back in time. And that's like a pretty important aspect of this and doing this work, is that you're using telescopes like a time machine to see back into the past, because these galaxies aren't just ones in our backyard. They're ones where we're seeing them as they looked when these galaxies were forming, which is fundamentally exciting. I think that I have, if you want to see one of the farthest galaxies that Hubble had found, it actually isn't the farthest. Please. I realize now that there's an even farther one that we confirmed with JWST, but this galaxy was very famous pre-JWST because it was for many years considered the farthest galaxy, a galaxy called GNZ11. It was called that because it's in GN, which stands for Goods North, which is the Hubble Deep Field North, is in a larger region called Goods North, which is the Great Observatory Origins Deep Survey, I think, which is a bunch of telescopes looked at that region with a lot of time. And they found this object. This was found by a guy named Pascal Oesch and his team. And it was something where it was anomalously bright and had a lot of the signs that it was really, really distant. And it was called GNZ11 because it was thought to be at what's called a redshift, which we'll talk about later, of 11. And we now know it's actually at a redshift of 10.6, but who's counting? And we have amazing spectra because we have JWST. But this galaxy was very, very important. And up to the launch of JWST, this was our earliest look at the universe. This galaxy was forming within the first, several hundred million years after the Big Bang. We're seeing it as like a baby galaxy in a baby universe. It was like really, really exciting. But that was the state of the art,
That's fantastic.
Mm-hmm.
And you can see even it's not just a single point. It's even a little bit resolved here. And,
yeah, it's neat also that we have updated JWST. We're not talking about it here, but we have updated JWST imaging. That is not an artifact of like some weird noise. It actually does have some haze extending off the top here. This is a real thing we see in the JWST image as well. It's a very exciting object. I could give a whole talk on GNZ11 because it's incredibly bright. When the spectrum for this object came down, our team was the one who got it. And like, I just remember everyone on our team, the sound of the jaws dropping, showing it, because I don't know if people watching are familiar with Jane Rigby. She likes to show it as like one of the great early triumphs of JWST is like, you just spend hours and hours from the ground trying to get spectra of galaxies that are so much closer. And then this one just comes out and it's like the most beautiful spectra we'd ever seen. It's incredible.
I want to remind people before I get too much further, feel free to drop questions into the chat. We're going to be taking questions kind of throughout. So if you have something that pops into your mind, just go ahead and drop it in the chat and we'll see if we can add it in. So this was Hubble's distance record.
Yeah.
What was limiting Hubble's vision before?
So let me talk a little about light. This is the part where for some of you watching, you're going to be like, I'm going to go take a little nap. That's okay. But for many people, this is a complicated idea. And I have a couple of ways of thinking about this. But like, light is a very important thing. Most astronomers, it used to be all astronomers, now most astronomers, because some astronomers, they look using waves of gravity and not waves of light, which is very exciting. But astronomers, the majority of us, we are light worshipers. We live to get light. And light comes in a lot of different forms. The light you're familiar with is this color right here, the optical, because our eyes are sensitive to it. But the light doesn't only just exist in the optical. There's light that has higher energy that our eyes just can't even see, UV or X-rays. Like when you go get X-rays, it's not like a thing where it's shooting some sort of fancy laser at you. It's just shooting a very fancy flashlight that happens to go through your body, but not your bones. That's how X-rays work, right? And there's gamma rays, get more dangerous versions of the same thing, right? And on the other way, you get the infrared, my favorite wavelength range, and then into radio. Your microwave, if you didn't realize it, is a very fancy flashlight. That's it. Your cell phone, another fancy flashlight. It's sending radio waves to a tower. It's just a fancy flashlight, except the light is not light that you can see with your eyes. It's light that can penetrate walls, such that your cell phone can work inside, right? All this is light. And the thing about light is that when it's emitted from an object, if that object is moving at all, it'll change the way we see the light. And so if we look here, this is another version of that spectrum where I'm putting little lines, which would indicate in a galaxy like absorption from certain chemicals, certain elements. Like, oh, might be like the green here might be oxygen. You see oxygen here, or you might see hydrogen over here, right? You know what these things are. But like these are like fingerprints that we on the ground can know where they should be, what colors they should be. And if the galaxy is moving towards us, then suddenly it will be blue shifted. All those little lines will be shifted towards bluer wavelengths because of the way that as something moves towards us, it's, you could think about it like the light waves getting squashed in wavelength space. And vice versa, if the galaxy is moving away from us, like pretty much all galaxies are, outside of a couple really nearby ones, most galaxies are being pulled away from us by the fact that the universe is expanding, which means that their light is redshifted and pulled to longer wavelengths. And so what that means, let's think about it. I have this other metaphor. Let's see if this works. Here's our same thing where I have UV over left, our optical, the rainbow we see in the middle, and the infrared be on the right. Let's just associate every color with a letter in the alphabet, right? So we've got, and this is helpful because the letters in the alphabet carry, like some letters are more important in the English language than others. Like A, E, I, the vowels, really important. Actual light with galaxies, the colors that you see, if you saw emission at that color, that would tell you something about hydrogen or oxygen. And the ultraviolet and optical are very important. As you get into the infrared, you get your stuff, your W's, your X's, your Y's, not as important for the English language. And similarly, in actual galaxies, what's called the near infrared is not as exciting. There's some people who would take issue with that, but I think that really a lot of the information is carried with some of these letters. And so like if you had a word, which was a galaxy, like begin, that's our word, that's our galaxy, you would know about what's going on in this, because you'd know begin has a B, an E, a G, an I, and an N. And that is what makes up the word, in the same way that those colors might tell you about the composition, the stars in the galaxy. If it were redshifted, it'd be pushed to longer wavelengths, which means it'd be at different colors. So instead of it being begin, the word would be degikpa. And you might get that word. It would be emitted from the galaxy saying begin. And then it would get to our eyes and it would have been stretched to longer wavelengths. And we'd hear degikpa. And we'd be like, what is that? But we know the universe is expanding, which means it's this far away, which means that the light has been redshifted. So I go, oh, I just take every letter and I subtract 2 letters from it. And I get back my original, like a code, right? If it were even farther wavelengths, this is where it gets exciting, higher redshifts, really, really out there, just flying away from us. Now it's Kutifix. And then the last letter is something that is beyond the Z. You could like imagine like writing numbers out there. So it'd be QTVX3 or something. But we can translate that code into what we would imagine if it were not moving and flying away from us. And all that is to say is that infrared then becomes of fundamental importance, because a lot of the things we care about, all this information that is encoded in letters, is shifted into the infrared outside of our ability to see. And the infrared Hubble, as a telescope, was limited. It had an infrared camera, a couple infrared cameras, a camera called NICMAS, and then it was replaced by a camera called WFC3. But they were like limited. They could only see, like, imagine, if this kept going, like maybe 1, 2, 3, 4, 5, I don't know, right? And then there was another telescope that launched called Spitzer, a lot smaller field of view than both Hubble and eventually Webb. That Spitzer was infrared and could see out in those wavelengths. So it had the ability to see at farther wavelengths and see some of these galaxies that Hubble could not see. And so, like, I can show you the same Hubble deep field. This is the Hubble good south. This is the Hubble ultra deep field with Spitzer. And you notice a couple things. One, and it sounds rude, but like the chat is telling me that neutrino and cosmic ray astronomy are pretty important. I appreciate it. Yeah, neutrinos not light. And cosmic rays, with charged particles. I apologize, chat. Thank you so much, Grant, for keeping me honest, because that is a very important thing. High energy scientists are all going to yell at me and I'll get nasty emails. I'm just a lowly infrared astronomer. Anyway, you see here that, and again, it's going to sound rude, but it's fair. The image doesn't have the greatest resolution. And that's because Spitzer had a much smaller mirror, and it's very hard to get resolution at long wavelengths. you can do better with resolution at shorter wavelengths. And, it's a little hard to do that. But it also wasn't as sensitive as telescopes to come, but it was our best way for many years. I have a lot of love for Spitzer. My first research projects were done using Spitzer data. I'm like, I absolutely love Spitzer. But you can see that when NASA decided, and along with the European Space Agency and the Canadian Space Agency, to go, what if we made Super Spitzer? What if we made a telescope that had an enormous mirror that saw in the infrared, that was incredibly cold? What if we put that in the space? Could we do better? And the answer is yes, we could do way better. We did that with JWST. So this, I'm going to slowly fade in on the JWST version of the same thing from JADES. And you can see the incredible, unprecedented detail. I'm not even zooming in here. Later I'll zoom in. But all of those smudgy blobs resolve out to be many, many galaxies. And between, there's all these other little galaxies. It's more sensitive, better resolution. And it really works in tandem with Hubble to find all these galaxies and understand them. But Hubble couldn't see really, really far away galaxies. And Spitzer couldn't see some of these fainter, weird things that JWST would see, which is what's setting up our idea of, what types of things did we see?
Yeah. And speaking of, this new, JWST image that you're showing here, it was taken with NIRCam, and you're a member of the NIRCam science team, so you were involved in its commissioning and its construction.
Yeah.
How did those early deep fields from Hubble shape NIRCam's design when you were working on NIRCam?
Yeah. So the thing is Hubble is a fantastic telescope with incredible instruments. I will say that one of the things that limited its infrared capability was that Wide Field Camera 3 didn't have the largest field of view. It had pretty good field of view. But if you were watching earlier this week with the excitement about the Rubin, first images from Rubin, that has an enormous field of view. And field of view allows you to see a lot at the same time. And so when Dr. Marsha Ricci and the UA team that she assembled were designing NIRCam, one of the things was, can we get a good field of view? And so this is the field of view of NIRCam. And as comparison, WFC3 is a little bit less than one of the squares here on the left, so the red square on the left a little bit less. And NIRCam has two next to each other, because NIRCam is two identical cameras. Well, they're mirrored, but identical cameras sandwiched together. And that's really exciting, because if one of them were to die, God forbid, we would still have another camera that we could do, Module A and Module B, that could take really great images. But that means you get these big rectangle images with some gaps where the chips are. And eagle-eyed viewers are noticing that there's a red and a blue here. And the red and blue are the fact that inside of each of those little modules, there's a little thing that's called a beam splitter that separates the light into and long wavelengths, which means that you can take one image at short wavelengths and one at time. It is in the lifetime of JWST, the discovery space will probably be really driven by both NIRSpec and MIRI in terms of the most exciting results. But the backbone of this telescope, the backbone, the bread and butter of this telescope, the thing that when we're looking back on this and we're looking at the beautiful images, comes from NIRCam. I've gotten to work with the NIRCam scientists, both at Space Telescope and at the University of Arizona. Brilliant folks who put together a camera that works so well. And all of the images that you've seen at home, the cosmic cliffs, all these things, they come from this camera. It's I remember seeing some of the first images with the team and just the emotions, because I'd seen it on the ground, I'd tested it through all kinds of, nasty, hurricanes and, global pandemics and stuff. And to have it take these images, it's incredible. The sensitivity, the resolution, the telescope works better than we even designed it to, it was, tolerance. And it's such a good camera. And it's this unique design. And here you can see a comparison between the Spitzer view and the JWST view of the same field. And it doesn't look it looks totally different. I mean, first off, Spitzer has this crazy PSF that looks like little triangles, little triforces. But this star right here, you're seeing right here, is literally just this star. Right? Tell it's a JWST image. It's got that beautiful nightmare snowflake there. But look at look here. You can tell there's a galaxy here, and you can probably tell its brightness in a couple bands. Spitzer had an image like you take images like 3 microns, 4 microns, and so you can get a couple bands. But here, you just get many, many bands showing that. And like, look at all the things that you can see between everything. It's crazy.
Yeah, this is really one of those pictures worth 1,000 words.
Exactly, right? Like, and nothing against Spitzer. Fantastic telescope. Really incredible, revolutionary thing. But sorry, this is the march of progress.
Yeah.
You know, and so if we zoom in, here is Jade's, like the survey that I work on, the JWST Advanced Deep Extragalactic Survey. Which was a joint effort from the teams that built NIRCam and the teams that built NIRSpec, the spectrograph. And this isn't even all of it. This is like kind of a zoom in on one part of it. And if I were to just like go forward, you could see that if we zoom out, this is the public version. The Good South. And as I'll show later, we have enormous amount more that's going to come out in our public data release in a month. It's a huge amount of data, and all of it is something, you know, that can be looked through. And by comparison, the Hubble Ultra Deep Field is literally a square right in here. The one that like back in 2000. Enchanted me and made me think, man, being an astronomer, what a wild thing. Like, is some tiny chunk of what is, and again, I'm not showing in this, I'll show it later, a huge amount of data that all of these galaxies, like we know so much more about them because of JWST.
When these images first started coming in 2022, we started getting images like this. Mm-hmm. There was a flurry of new science papers that even in that first week being posted. Yeah. What was jumping out to you and other astronomers just right off the bat when you were starting to examine this data?
We got our JADES data a little bit after some of the earliest data. There was data that was taken as part of the early release program in terms of like that beautiful image of the lens, the harbor parking lots in Baltimore, so near Space Telescope. And like, if you look down at this, there's like these big blue things, which are strange. There's all these little tiny things that are like, some places they're very dense, and then right next to it, there's like a big void. And there's these big circular things down here that don't look anything. There's this weird channel that, you know, what is this? If you were an alien trying to make sense of this, it'd be very complicated. And then similarly, when we got our first JWST data, we were looking at these and we knew something about some of the galaxies, but many of them had never been seen before at all, especially at these wavelengths. And so one thing that we were looking through, and I remember with my student Jake Helton, we were looking through and we were giggling because we kept finding weird red things. And we're like, what is this? This looks like nothing I've ever seen. And similarly, like when you look at this image right here, you could start identifying weird red things if you were an alien. Like, I'm putting circles around most of the weird red things and be like, what is this? If I didn't know what these things were, I'd be like, some of them, a small fraction, but a lot, are red. Most of them are white or black, and then some of them are red for some reason. What are these? And you might put them into a folder for what is this for later, right? And that's what we did on the team, along with people around the world. We were like, what is this? So I'm going to show you a recreation. I'm going to kind of like, this is a video that's me kind of dragging our way through our FITS map. But like everyone watching at home, find the thing that we found that was exciting. Luckily, it's right in the very center. This thing right here was one of many things we were finding. And if we just zoom in right here, this object right here, which has its telephone number, and then we have an internal ID number, was one of a bunch of objects, many, many, that we just put aside as like, what are these things? What could they be? And this was something that like was going to set science on a crazy, crazy, like exciting hunt for the next several years. Was all the teams in the world looking, because it wasn't just in JADES, it was in almost every field, we were finding these things that had never been seen before. Couldn't see them in Spitzer data, couldn't see them in Hubble. What are these things? Really red, really compact. These little red dots.
Yeah, and you found a huge number of these fairly quickly. And what made them different from the other kind of galaxies that you saw? Why?
Yeah. So you can see partly here that, galaxies, this one's green, there's like, galaxies don't end up being this red, and they're especially compact, really compact. So compact that many of them look like a little rose in the imaging because they are what's called a point spread. They're so compact, they're unresolved, meaning like, how stars in JWST images have these crazy spikes? That comes from the fact that they're not resolved. We don't see them as a star. They're like so far away and so small compared with how far away they are that on the sky, we can't resolve them as a little ball, which means the light spreads out in a characteristic way through the telescope. Similarly, these objects are doing the same thing. So there's a very important paper, the paper that coined the term LRDs by Yorat Matei, and this is a plot from Yorat Matei's incredible paper. This is the one that was like, little red dots, what are these, essentially? And you can see these are objects from, in some cases, JADES data in Goods North, and in other surveys, and technically it's fresco data from Goods North. Which is part of JADES, but I don't want to get into that. I just don't want someone to email me frustrated. But you can see, look at this one. It looks like a weird rose, like a flower. And that is, those are the spikes, the baby versions of the spikes, as if it were a star. And this is a really exciting paper because it was a very early on paper that was like, these things are crazy. And they're crazy because as part of these surveys, they had access to a very NIRCam. One of the other cool things about NIRCam is it has an ability to take a spectrum, to pass its light through a prism, essentially, such that you can look at it as a function of wavelength. And they could look and see what's going on with these objects. Are they really at the distances we think that they could be? And Yorat and other teams in other papers, but Yorat's is the most famous, discovered this idea that if you pass the light through a prism and look at hydrogen light, this is light here from hydrogen gas, you see that the hydrogen gas has these broad bases. So this is shown where the x-axis in all these plots is velocity, because the velocity is what's taking the light and spreading it out, because the gas is moving really fast. And the gas is moving thousands of kilometers per second. And the only thing that we know that can get gas moving at such fast velocities while it's doing that is potentially a supermassive black hole. So this was a really fundamental thing. Yorat Matei was like, these objects are crazy colors. They're very compact. And they've got, for many of them, most of them, really broad emission lines, broad hydrogen. Like this is H alpha, so it's a very powerful hydrogen line. And you can see it's very broad. Up here is you can even see the little wings off the center core. Those wings indicate something is going on in this that's really, really wild. And so the other thing about them was that if you take their light and looked at them in all the different filters that JWST has, they looked wild. So here's another example that I pulled from Jade's. It's got its telephone number, it's an ID. And if you look in the rest frame UV, it looks kind of like a little fuzzy galaxy. But if you looked in the rest frame optical, it looks really, really red and like a point source. Combining that is what generally we were looking at when we were finding them, but you can separate, because JWST, especially with our survey, Jades has a lot of filters. And so you could say, only show me what it looks like where we color it, just like the shortest wavelength filters and then only the longest wavelength filters. If I were to take the brightness in every one of the filters and put that on a plot, that's what you see here. The red points are all the brightnesses in the JWST filters are the dark red, and there's like these pink points from Hubble. And this characteristic shape where it's kind of flat in what's called the rest frame UV, and then suddenly it rises towards the optical. This is the V-shaped, I mean, it's a really open V-shaped SED. And this SED stands for spectral energy distribution. It's just plot all the data you got as a function of wavelength. And so these are all individual NIRCam filters that show us this is a crazy odd UV, like a galaxy, with something else going on that is making it really, really, really red. Very strange. And it set off a huge flurry of papers where people were like, let's find them. Here are 3 papers from Pablo Perez Gonzalez, which has some Jade stuff. You can see my name right there. This is about what is the nature of these, the rise of faint red AGN. This is a sample of little red dots. This is Dale Kosebsky's incredible paper that tried to collect them across a huge number of fields. This right here, Jenny Green at Princeton, and some other team members were like, let's try to see, do they all have, how many spectra can we get? Do they have a bunch of broad lines in them? And found, yes, it's ubiquitous, these broad lines. There was a huge flurry of, and at the very core was this idea. What are the ways in which this galaxy could be this red, to have this crazy red slope, this V shape, really compact and red? What is going on with these objects? And quickly, a bunch of scientists were like, well, I mean, what's great is the way that science works is people go and they discover things. They go, what is this? Then a bunch of theorists get really excited because they open their computer programs up and go, time to simulate some weird things. And they say, I think it's this. And then a bunch of paper comes out, I think it's this. And then the observers go, well, if it's this, we should be able to see this. And it's circular, right? So I'm going to present some of the things that theorists and other scientists thought were the case. What's going on in this? So wait, lights just turned on, which is very nice. Could be, like I said, dust heated by a supermassive black hole. Maybe we're seeing hot dust, really hot dust. It'd be very crazy. Maybe they could have a bunch of dust that is covering, and so you can't really see it because like the dust is a very strange thing. Maybe it's like a quasar that's a really strange dust distribution, and the dust is blocking our ability to see some of the shorter wavelength light. Maybe that's what's going on. Maybe they're red, not because of dust, but because they just have older red stars, and they're a really old, massive population. This is a very, exciting idea, because the universe is only like less than 2 or 3 billion years old when we're seeing these things, which means that we'd have to have like some population that like grew really massive and then shut off early on in the history of the universe. Or finally, as with every astronomy theory, it could be something else entirely, right? So this was like some of the main things. Papers were coming out being like, well, these are what we think it could be, right? And there were some pretty big papers that said a couple of these really, really big, like really, really, like publicly, they were like, really, this is what it's got to be. And they did fits with this. And that ended up getting a lot of traction.
Yeah. So that kind of leads in, I guess. Have little red dots broken cosmology? Have they broken what our universe is?
For the first two, if they are these things, then that there's ways we could explain it. This third one, that they could be full of older red stars, like that would be a thing that would be very difficult to understand in our current framework for how the universe worked, because we think that galaxies grew in a very characteristic way that Hubble has shown us and JWST has shown us. And the idea that also galaxies were growing really fast and then dying very early in the history of the universe, that's a lot. And when this came out in the media really seized on this, being like, JWST has found these red monsters. I just like very easily found like a bunch of these, evidence of massive galaxies that defy theories, surprisingly massive galaxies from the universe. 6 massive galaxies so old they can't be explained by science. They can't be explained by science. I love these headlines. I'm showing these also for the people watching. Watch out. It's really exciting to write headlines like this because it will get people to click. People love when scientists find things that can't be explained by science. I'm about to show you a bunch of slides to show that we can explain these things by science. That's the whole point of science. It's a very cool tool that allows us to explain these things. And even if they were this massive like this, we would have to revise our science and explain them by science. Science is not like, science is not the truth. Someone is asking, I got a really good, okay. There's a good question or so. That's good.
We can hit it.
Yeah.
We have a question from the chat. Is Webb still taking questions from the scientists around the world?
Oh yeah.
Or is its dance card filled up?
No. The way that his dance card gets filled up is once a year. There's a huge call for proposals that's generally at the end of the year. It's incredibly competitive and incredibly difficult to get time because a lot of scientists want to use this amazing telescope. And you can see the next February or March or something like that who it gets picked. You can look it up. It's called the GEO. Like this last was cycle 4, and this fall will be cycle 5, and a bunch of scientists' time will be taken up. And so it's every year. And every time there's a call for proposals, Space Telescope, who's running this whole thing, will come out and say like, hey, here's the capabilities we want to use in the telescope. Here's what's going on with the telescope, and then you write proposals. And it's a really, really exciting thing, but also it's very competitive. And so, you write the best proposals you can, and luckily the teams have done a pretty good job of picking great stuff. But it is the dance card is once a year. So I think it's a good question. And it's good for us. It's good because if we had filled the dance card out, then when we discover new things like this, we can't go back and figure out what they are. And so I'm going to show an object later that's from a program that was designed specifically as let's follow up weirdos. Like the program is called Miracle or Mirage because it was like, these are weirdos. They're either a miracle or they're a mirage. Like, the new distance record, breaking the James team's record, my own record from a couple weeks ago, is from that program. And so it turned out miracle. And then another object I'm going to find, another miracle. Seems like the Miracle Mirage team did a really good job choosing miracles, which is great for them.
Yeah, I love that this is such a clear conversation between different science.
And we look for them and we say, we've got to go after these. And we look for them and we say, we've got to go after these. And there's ways in which you can get time pretty quickly to follow up some of these without having to go through that yearly cycle or you are designing a program where you're like, oh, at the last minute, we can add a couple objects. NearSpec, the spectrograph on JWST, has a mode where it can take a lot of spectra at the same time. Generally, it starts by looking at NearCam data for V-shaped SEDs. That's what you're looking for. And so imagine we go back to this idea, this thing here. This is a weird metaphor. When you do this, if you just start going like, okay, everything that I've circled in red must be the same thing, you're going to be wrong, right? That's because you all know watching, these are cars and trucks. But cars and trucks that are red aren't all the same cars and trucks. And in fact, if I like zoom in on one of these things here, like this is a very different version than the other red one down here, right? This is not a truck. Like, or if it is, it's a very strange, like it's very compact. And you have to watch out when you just take and assemble a sample that you're assembling the same types of objects. So I wrote this paper that was at its very core being like, A, if these are supermassive black holes, they're not the whole population of supermassive black holes, but that's aside from the point. B, be very careful about how you select them. So here's a plot for my paper. Every one of these objects on the right was selected by multiple different authors as an LRD, as a little red dot. But all of these objects have very different underlying reasons for why they look that way, why they have this V shape. So you can see a V shape that kind of like goes up here, or a V shape. This one on the top, the red one, that's classic LRD. Maybe this yellow one as well. But the green and blue lines below it, most of what's driving the LRD is uncertain, and it's the fact that there's gas in these galaxies that's emitting a very specific wavelength, tricking you into thinking it's a V shape. But it's not. It's just gas a specific way, oxygen gas and hydrogen gas. And you got to watch out for that. And similarly, at high redshift, oxygen gas can really, really affect that. And then there's other objects like this blue one down here, which is a lower redshift, and it might not be the same as what you're seeing up here. This is like a very important thing, that if you want to understand these objects, you can't just lump everything that looks like a little compact red thing with a V shape together. And more to that point, let me show you a couple of these LRDs. Here are a bunch of LRDs that we found early on. I am looking at these. We post them. Someone in our Slack posts one of these objects, and it goes like, "What is this?" And we're starting to look at this. Maybe it's one of these. Maybe it's a black hole, whatever. And I realize almost immediately when I see this, and along with credit where credit is due, another person working on James Feng Sun, who's at Harvard right now, he and I both are like, "This is not a galaxy." And I subsequently collect a lot of these objects and write a paper on it, because what we're seeing with these is a V shape of it, a very special, weird V shape. We're not seeing from a galaxy, we're seeing a brown dwarf. And so this right here is what a brown dwarf is. Between a planet like Jupiter and the sun are like, we call them failed stars, but that's so rude. I just think of them as excited Jupiters, right? Like real hot Jupiters, very, very hot Jupiters. They don't have the fusion in their cores, but they are, so they're not making light, but they're still cooling off. And they're, in some cases, very, very, very cold. Like this one down here is at a temperature of 1150 Kelvin. I have ones in my sample that are down to 700 Kelvin, down to even 400 Kelvin. I have some of my samples that are cooler than the coffee I drink in the morning on their surface, right? And we can see them with JWST because we have incredible unprecedented sensitivity. But look, here's the V shape. You see the same V shape. They were picked up, but this V is too blue over on this side. It generally has to be flat. And if you threw these in, you'd be like, what are these? And in fact, people got spectra of these objects, thinking they were other weird LRDs. And I had to be like, actually, you're going to get brown dwarfs. And then people wrote quickly papers on the spectra of these brown dwarfs, because these brown dwarfs were incredibly distant. Some brown dwarfs that were in the halo of our galaxy. And I love this article here that was written about my paper, because it says that they were accidentally discovered. And it was not an accident. They were accidentally initially found maybe as part of another thing, but I went and found them on purpose. And I'm writing another paper that's going to almost double the amount that we have, some incredible objects that are well outside the Milky Way, at the very edge. And it's really incredible to think about that in this one survey, we have these ultra distant galaxies, but also we have the ability to probe the makeup of our own galaxy just with little interlopers that are kind of moving through, which is very fun.
That's really amazing, just because, brown dwarfs are about as far from a galaxy as you can get, right?
Yeah.
It's not even a collection of stars. It's the smallest star. Yeah. It's not even a star. It's so small.
Yeah. I got in trouble when I wrote my paper. The referee was like, you should not call them stars. They're not stars. Stars have fusion. I think if you were to take, I wrote, right after writing this paper on this, I wrote another paper on galaxy redshift of 13. And I think if you take the farthest thing, at ratio from farthest thing you've written about to closest thing you've written about, I might have I might have one of the highest ratios, because it's just, I guess I wrote something about the moon or something like that. So I need to write about something that's even closer. But the fact that I'm writing papers about brown dwarfs, it's so fun. I love working on JWST data because there's just new mystery after new mystery.
So here's a question from the chat: is how do you differentiate between the brown dwarfs and the little red dots? Can you do it without spectra, or do you need the follow-up?
We don't need the spectra. I have spectra for a number of them, which is a really nice thing. One of the ways is this. There's you can see over here on the right that at this filter to this filter, it's fairly blue. That's a way. Also, the blue of the filters over here on the left, meaning it slopes upward as you go to the shorter wavelengths. That's not seen in galaxies. It would indicate the galaxy is making a huge amount of stars that we do not see. But more importantly, and the real way, the way that I convinced, because I messaged Jenny Green about some objects of her paper, and I said, these are brown dwarfs. And she's like, how do you know? And I said, well, we have some in ours. And she's like, well, how do you know those are brown dwarfs? Exactly as the person in the chat just asked. And I said, well, because brown dwarfs are close enough to us that if you look at them with Hubble, and we can see some of them at the shortest wavelength with Hubble, and then you look at them with JWST, decades have passed. And they are close enough that they're moving. So you see what's called the proper motion. You can blink between the two and see them moving. Galaxies are too far away to move. And we even have ones where we took a picture with JWST, and then a year later took a picture of JWST. So it moves there. And that's pretty exciting because we see this motion, and that motion is called proper motion, and it really, really cements that these are brown dwarfs and not distant galaxies. And when you fit with models, like I have a galaxy model in green here, it fits really, really poorly. But the brown dwarf models fit incredibly well. And I have code that I wrote. I'm plugging my own code that's going to come out in a couple of months called Nifty, near-infrared fitting for T and Y dwarfs. It's like a Bayesian fitter that fits these objects super, super well with publicly available models. And it's very exciting. So if you are someone who is watching this and is like, oh, I got all these brown dwarfs in my sample and they're contaminating, I'm like, they're not contaminants. They're exciting. Here's a code that fits them. You can write papers. Get an enterprising graduate student and hand them my paper and say, do that with our data.
We have a question from the chat about brown dwarfs. Are they actually brown? Why is it called a brown dwarf?
Yeah, so they are it's hard to say. Like when it comes to color, like they are actually predominantly cold enough that like they're not emitting a huge amount in like what we can see with our eyes. Like they often emit a little bit longer wavelengths and they get very red in the infrared. But there's a lot of absorption. It's kind of like, think of it like a Jupiter, right? Like think of it like a Jupiter, maybe a little bit. So there is some brown because of the chemistry in there, maybe a little bit hotter. Like I do like this image here, right here, where it's 13 to 80 times and it's a little bit redder or a little bit purpler or whatever. Like that's kind of what you could imagine. But again, for most of these things, it would look different if you saw it with your own eye than with our telescope or whatever. But like these artist renditions here are fairly good renditions with these clouds and these bands and stuff.
Cool. So we know now that little red dots could be, several different things at the same time to manifest. What's your preferred explanation for most little red dots right now?
Yeah.
And what would convince you maybe that you need to think a little bit more?
Yeah, so let's just go through some theories and stuff, and I'll talk about what I think is a really, really good paper that, like, among many other papers that have come out about this, but like I think demonstrates what I think is probably going on. One of the exciting things about these objects is, as I mentioned, we don't see them close by. So this is a thing where when Dale Kosevsky and his team assembled this enormous sample of them, he was surprised that they were not seen below generally a redshift of 4. And so I put a red dashed line here at 4. There's some, but generally it kind of falls off, And that is exciting because redshift is not linear. So redshift 10, 8, 6, 4 is like half a gig a year to like 1.5 billion years after the Big Bang. Meaning, like, once 1.5 billion years of time after the Big Bang happened, we stop seeing these things. So whatever this is, it's a very short-lived time in the history of the universe, so just a couple billion years, where these things existed and did something, right? And that like tells us a little about what might be going on. And other scientists have kind of followed my lead. This is a work on the left from Raphael Wieding, who's a researcher in Europe, that in this survey, they have a bunch of cool spectra. They can say, well, these ones are LEDs that have the V-shaped SCD. These ones are really compact. These ones have the broad lines. And it's not a one-to-one Venn diagram. It's not everyone has all of them. This is essentially, when I emailed him, he's my former grad student, so I'm close with him. When I emailed him, I said, like, this is incredible work. Nice job, Raphael. And he's like, yeah, well, I saw your paper last year and thought we should be doing that. We should be thinking about these things as not one species, but like multiple types of things, right? And other theorists like Gillian Boulovery here have been really trying to understand maybe what this is that early on in the universe, you have black holes in very dense gas environments where you get gas falling on, making these tidal disruption events where the gas is being ripped from, the cloud and just like falling onto the black hole in these things. And that's what we're seeing, these tidal disruption events, which is exciting. Or some people have claimed maybe it's not a black hole at all. Maybe you don't need a black hole. Maybe to get these broad lines, you just need stars that are very, very dense in dense environments, and they're kicking gas around really fast. And so this is a paper by Josephine Baggin saying the small sizes and high implied densities could explain their broad emission lines without an AGN, which would help because it'd mean that's why we don't see X-rays. That's why we don't see these other things, because it's not actually an AGN. It's not a supermassive black hole. It's just dense stars, right? I'm showing Wiki 18, which is a nearby local universe analog, I think, to some of these very dense, weird regions in the high redshift universe. So someone asked me what an SED is, and an SED is the spectral energy distribution, and it's when you right here I'm showing the SED in these red points where you take every picture that we have and every filter from JWST and you just plot how bright is it in that filter, how bright is it in that filter, how bright is it in that filter. And when you do that, you see that it has this V shape where it's bright over here at around 1 micron, then it falls off around 2.5 to 3, and then it gets bright again. So spectral energy distribution, like if I go back all the way up to the front, this is the spectral energy distribution for an actual LRD, where all of these red points is one image with JWST showing it's bright at 1 micron and then 1.15 microns and 1.5 microns, 1.8, 2.1, 2.7, 3.5, 4.1, 4.4. Nice job, Kevin, knowing his NIRCam filters. And all of them together, you can fit models to that to understand what it is as a function of wavelengths. That's the SED.
Great. And there's also a question about your timeline about what the GYR stands for, the gigayears.
Oh, gigayear. Oh, sorry. It means billions of years, excuse me. And so like this is 500 million years, so a gigayear. 1.21 gigayears, 1.56 gigayears, 0.48 gigayears, 0.48 billion years, so 480 million years, 650 million years, 940 million years, right? So this tells you at the very beginning, GNZ11 was found essentially over here. And so again, 300 to 400 million years after the Big Bang is when we're seeing it. And we're seeing most of these LRDs when the universe is only about 1 billion years old. Pretty cool. So let's talk about what I think is maybe the forerunner theory, a pretty good theory that starts with this miracle or mirage or miracle survey. Rohan Naidu and a bunch of really, including Jorrit Mate and a bunch of other important, Anna de Grasse on this, people you've seen, Pascal Oesch, who's discovered GNZ11, a lot of familiar names on this paper. He finds this object that is really wild because it has what looks like only just the V shape on the right. And you can see it's this blue thing here, where it's incredibly flat and then suddenly rises as you go to longer wavelengths. And what he hypothesizes and then models this as is a black hole surrounded by incredibly dense gas. And if there is dust, it's maybe just a little bit, but not a lot of dust. And that incredibly dense gas is feeding the black hole faster than it otherwise might be able to feed. So it's a super rapid feeding black hole, growing black hole in the early universe that's surrounded by gas only. And that is causing this crazy blue bump here from the gas emission. The gas is being excited from that disk of gas falling on the black hole from the disk. It's exciting that, causing this blue emission here and this absorption. And then it's inside of a galaxy, which they just took a galaxy nearby this object in gray and said, what if we add a nearby galaxy in gray to the blue that we observe from this object, and they get the red. And so they take the gray of the nearby galaxy, which is has young stars, is making UV. They take the red of this weird object they call a black hole star in the optical. They combine it, and they get the red, which looks like an LRD. There's the V shape right there. And this is what it could be. The reason there's no X-rays is the X-rays are completely enshrouded. The gas blocks all the X-rays. If there's dust, it's very compact, or there's not a lot of dust. And if you do this, there's not a lot of dust, which means that you're making corrections to measure how big that black hole is, and all your corrections are going to be wrong. They're going to make the black hole seem more massive. This would solve almost all the problems. In his modeling of doing this, when he did the models, this blue line, it also goes and then flattens out, just like Christina Williams' research. This is a very good model that has been other members, Jorrit Mate's paper, Jenny Green, Bing-Ji Wang, they've other papers have said yeah, this is a pretty good model, or they came out before and had similar ideas, which is what if it's a very dense environment around a black hole of gas? And that is a pretty good explanation, I think.
I like that also kind of explains why you don't get them in the local universe, because you need dust poor stuff around it. So
exactly. You don't have the same types of environment in a local universe due to high redshift. You need very dust-free, very dense gas around these growing black holes. And black holes have a long time to grow since then. They're in the centers of all massive galaxies. But this is a pretty good explanation for how you get big black holes in galaxies in the nearby universe. You grow them early on in this very crazy environment. And so that's maybe what we're seeing. We're seeing some of the early black hole growth that would seed large galaxies going down the line, which is pretty exciting.
So we have a question about the picture here, about why is it blue?
Oh, the thing up in the top right, or the thing down here? The thing down here is blue.
Right,
the thing in the top is blue in the top right because of the HST filters and because it's making this object, 1Zwicky18. This is not an artist rendition. This is a real HST picture of an incredibly cool nearby galaxy that is kind of an analog for what we see in the high redshift universe. It's not exactly, because again, there's a lot of different properties, but it's like a thing that has a lot of baby stars. And the baby stars, if you take and make a big group of stars, the brightest ones are blue. They light up the gas around them with ultraviolet and blue lights. That's why they look blue. Over time, those blue stars die, leaving behind the red light from older stars. Good question, though.
So we have another question coming in. Does the size of the little red dot matter in what you see in the data?
Yeah, so mostly these little red dots, they are unresolved, meaning we don't know the size, right? That's why they're little point sources. They're designed to be unresolved. And so the size we can measure generally comes from if we can see the galaxy around them. There's some work being done by a researcher who's on the JWST team, Pierluigi Rinaldi, that I'm not going to show, but he thinks he's found a nearby analog where there's a big spiral galaxy and then a little red dot that might be growing something, or maybe at the very end of the cycle where we're still kind of seeing that. And that's pretty exciting. But generally, all of these things are unresolved. They're so small compared with the galaxy around them. I mean, they're really big and compared with humans, but compared with the galaxy around them, they're so small that we're just seeing them as a little point source. They're like just a little tiny nothing. And so we can't tell the size because we don't know the size.
Let's see. Oh, there's an image below the graph. There's a question about what does black hole dominated mean?
Yeah. So
BH dominated.
BH dominated. Yeah. So this is showing the galaxy in gray, and then right here you have LRD, 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 where essentially if you look at different wavelengths as you go from left to right in this, you'd go from being galaxy dominated, which is the left one, to a mixture in the middle, to black hole dominated, because you're only seeing the light from here. So like this red line kind of falls down, is a combination. It's a fake galaxy image down here of a galaxy combined with this black hole star, this object that Rohan Naidu found. And it's a thing where if you add the blue and the gray, you get the red. And as you march your way left, you get, over here, it's the UV dominated from the galaxy. So it's galaxy dominated. And now it's dominated by that light from that dense ball around the black hole.
Great. So how is the community using the large data sets collected by Webb and other telescopes, including through JADES and other programs, to work on new questions?
We have so many amazing JWST data sets. And like, I'm going to show you here, this is the larger version of JADES. And like, it's actually even bigger than this, but like, this is, showing like what I showed you earlier is just like a small chunk of this, but we have all this extra, and then there's other data from NG Deep and these other programs. There's so much JWST NIRChem data, and a lot of JWST NIRChem data that's not designed to like focus on one thing. It's what's done in parallel, which is, I think when we think about JWST in like 20 years, the parallel data that was taken while we're observing something, we turn on NIRCam and observe a field, a blank field nearby, and just get data that data has such incredible use and allows us to find these extreme things. Rohan, this object requires you to look at a lot of objects to find this very extreme type of object. And so this is something where by having larger area and adding an extra new data, we really can start understanding this, because we want, this has been the Wild West. And we're now settling into a new mode of JWST science, which is very exciting, where we're not scrambling to find all the low-hanging fruit, but we're saying, all right, we have a mature population. What's the way in which we can really go after the things we think are exciting, that we think are real LRDs compared with brown dwarfs, compared with, emission line galaxies, these things that like, oh, this is something that like we can't explain, or that would help support some of these other theories. And that is going to be what's going to happen over the next, several years. There's going to be even more of these proposals in the next cycle of JWST to go after these with other instruments. People have been proposing for other telescopes, like, oh, now that we found this, can we go see X-rays? Can we go see, and that's what drives science, is explaining these sorts of things. This has been really exciting as a person who studies supermassive black hole growth and AGN, to like, AGN science was for a while was thought of as like kind of niche. Like people were like, well, that's exciting, but like those are just contaminants. Now it's driven a huge amount of JWST science and proposals and led to a lot of very cool new papers and new studies. And it, doesn't break cosmology, but it really helps us understand how black holes grow, which like, I don't know, I think that's pretty cool.
Absolutely.
And, you should look out for the JADES public data release in a couple months. It's going to be really exciting. And I'm going to show you can right now, I just went through some of our public data release just last night on a lark when I was making this slide, and it was like fish in a barrel. Like these two up in the top right corner are like, they're located this far away. Like some of these are like multiple images, but these two are like right next to each other. Like, and that's very exciting, because if they're near redshift, they're actually concurrent, and that like might tell us about how they grow, because maybe they need others to grow around them. And like it's so fun to hunt for these. And to that point, if you want, don't do it right now because you're watching this, but right after this, point your browser to jades-survey.github.io. You'll find our FITSMAP software, where you can just go through, like Google Maps, like the top-down maps I was showing you earlier of the Baltimore Harbor, and hunt objects. And you can click up in the top right corner, this little hamburger icon, and click the SED. Now they know what an SED is. And every one of those objects will have a plot where you can see V-shape, what's going on. Pretty fun. You can collect them yourself. There's way worse ways to spend your time.
So we've kept you for an hour, but if you've got time, we do have some more questions from the audience.
Yeah, let's go through some questions.
Perfect, you're good to stick around. So one came in, how are proposals coming in from scientists selected? What's that process like?
Yeah, so what's exciting is that we have so many years of doing this that we know that there are pitfalls when it comes to biases that are inherent in this. And so what we do now is we assemble a group of, Space Telescope Science Institute assembles a group of scientists. Those scientists meet to discuss a lot of proposals. And those, sometimes they meet virtually, sometimes they meet like in groups, and they get proposals in an anonymous way, meaning they don't see who wrote the proposals. And you have to write them such that you're not being like, Heaven Cane line, like you can't hide. You have to like really make sure it's anonymous. And so you talk about, when I write proposals that are following up objects, I go like, wow, this paper by this guy who has some cool objects to study. And like, luckily, a lot of people are going to go after those same objects. So it's not as obvious. And they rank them. They read them carefully and rank them. And then you look at how much time you have and the rankings after much deliberation and discussing. And it's something where you have to recuse yourself if you can't sit in a panel where you look at your own proposal. That's also a bias. So you have to recuse yourself for those. And then after they're ranked, you look at how much time you can assign, and then that gets assigned to there. And then it becomes everyone's either most exciting day of the year or least exciting day of the year, because you want a lot of proposals, and the acceptance rate is fairly small because there's only a limited amount of time. And so you'll get a lot of rejections, and it feels it's a bummer. And it's sometimes disheartening and sometimes exciting, and it's very fun because these data are proprietary for different amounts of time, meaning that the scientists who propose for them get them to themselves, and then they become public. And in 5 to 10 years, you'll be able to go through all of the data that people were like ringing out. Like Jade's data is about to be almost entirely public. Not just that, but we've reduced catalogs and images and stuff so that you yourself could just go through and like look at the same objects we do. You want to go find the farthest galaxy? Go find it yourself, right? Like, and that's good for science, because goodness knows I made mistakes, we've made mistakes, and we've overlooked things that other people might have found that are exciting. Good question.
I have a question. What is your favorite brown dwarf you've ever found?
Yeah, so my favorite brown dwarf is 1904113, which is JWST BD5. I'm going to show it to you. Hopefully, I'm going to stop screen presenting, and I'm going to start presenting another screen. Okay, share this window. So this you can all see, hopefully, this is the FITS viewer that I was telling you about. This is the public website, meaning that you can just like Google Maps, you could just zoom around and you can go, look, there's the LRD. Look at this crazy train wreck of galaxies next to it. Look at this like blue galaxy. This LRD right here, you can very easily go and click NearCam SEDs, and every object gets a little circle, and click on it. And you see that it has a crazy SED, meaning I don't see it in all these filters. And suddenly at 1.15 microns, I see it. And then it becomes booming, incredibly bright. And this right here is indicative of the fact that this is one of the coldest brown dwarfs across all of JADES. This is what's called a Y dwarf. I have a spectrum for this object. When we had a program that I was a part of called OASIS that got spectra following up a lot of galaxies, I am on the OASIS team. I know the guy really well who built the OASIS mask, and I said, hey, can you get a spectrum of this object with OASIS? Yeah. Can you just like put it on? And he did. And then I was sitting with the team in January when the data had come out, and I said to our person, this guy Stefano Carniani, who reduced it, can you reduce 1904113? Can you use BD5 spectrum? Because like I think it's a brown dwarf, but I just want to see if we got a good spectrum. And he was like, oh, it's not a galaxy. Why would I do that? It's not a waste of my time. He's joking. But then he reduces it, and when it came up, everyone in the room, we had it projected, like started cheering because it was a brown dwarf, and it was a brown dwarf that like really showed that this object is probably like 400 to 500 Kelvin. Again, this object is an object that it's not super far away, but it is something that like, and I was seen with Spitzer data, but it is a very exciting object, and it has implications for really distant brown dwarfs. And so this one's my favorite, BD5. It looks like any other brown dwarf across the field, though. You wouldn't know. This was the one also that started my search for brown dwarfs. This is the one that when we saw that spectrum, everyone just flipped out, in the Jade Slack because it was just so crazy. But yeah. But again, if you haven't, like this object right here, this galaxy, you can just go click and see, and you'll say like, oh, what is it? And like, there's its spectrum. Here's its redshift right there. This is the predicted redshift, 0.55. Really exciting. And then like, we can zoom out. Just let's see if I can do this one more time because I have a lot of love. Right here, up until a couple weeks ago, this orange thing was in fact the world record holder farthest galaxy humans have ever found. This is JADES Z14, a galaxy that has a redshift of 4 points, a little bit less than the predicted here, redshift 14.18. And it was until, again, Mom Z14 beat its record by a tiny bit. It was the record holder, and it's a really, really amazing object. And it's, just right here in public data. You can go look for it right now. Like, it's really, there's so much to look at and see, and it's really fun, And as a hint, if you go up here, you can remove the word public from the URL, and it gives you the same thing, but now you get all of our individual filters and all these individual wavelengths. So you could look at it in different wavelength combinations and really, see the universe in different light. Like, what's causing this green? It's very, very exciting stuff.
Very cool. Oh, there's a question about black holes. About aren't they black? Don't they not emit light? Why are they included? Why are we saying that these are black holes that we're seeing?
Yeah. So black holes are, you're right, black. They are a big gravitational source that if light gets close, gets sucked in. And they don't emit any light themselves, but they've got strong gravity, and that gravity affects things. And black holes are messy eaters. They are not quietly little eating, like when things fall out of them, that it forms a big disk around the black hole. And that disk has to give up energy, or else it will just continue orbiting forever. It has to give up energy so it can fall into the black hole. And generally that's through friction with other particles in the disk. And that friction heats that stuff up. The disk gets very hot and glows in the ultraviolet. So the black hole is black, but it's surrounded by the disk of the stuff that's falling onto it. And that disk glows so bright, it's ultraviolet, gives off X-rays. When we first were seeing these things in like the 60s, they look like stars, some of these objects, quasi-stellar radio sources. That's, quasi-stellar, like a star, giving off radio. We're like, we don't know what this is. And quasi-stellar means like a star, but we shorten that to quasar. And these were very bright, so bright that disk, we were seeing the disk, it was just a little point source, and the galaxy, we couldn't see the galaxy around it. And in our Milky Way, if the Milky Way were the size of America, let's say, the black hole at the center of our galaxy, Sagittarius A star, its sphere of influence would be like a pea in a grocery store in central Kansas. Like that. So imagine that when you were looking at America from space, all you saw was light from that pea. That's what we're talking about. So the black hole is acting as a gravitational engine. It's black, but it has a disk that's glowing incredibly bright. And that disk, if it's surrounded by gas falling onto the accretion disk to fuel that disk can also cause the light that we see with these little red dots.
That's one of my favorite surprises from the last couple of years with Webb, is being able to see so distant black holes that are not swamping out the light of their galaxy, to be able to see the difference. Oh, I can study the galaxy and the black hole at the same time, and it's not just drowned out. It's really cool that we have the resolution and we have the ability to pull out, that we can see all of these growing supermassive black holes. Like I am a person who spent a lot of time thinking about the way that enormous energy source can have an effect on the environment and the galaxy around it. And we have, with JWST, we have really cool ways of, my graduate student, Sophie Leibowitz, has done a lot of stuff looking at the types of giant emission regions that are lit up by the black hole, like 9 billion years in the past, which is very, very exciting. Maybe one last question. Have we solved, or are we getting closer to solving, the Hubble tension between
This is a very different question the answer is, it's really complicated, and it depends on who you talk to, and it depends on who, and so I am not the expert on Hubble tension. Like, that is a cosmology, like theoretical physics thing, where I'm a person who thinks of himself as I love looking at galaxies and finding galaxies and stuff. And the Hubble tension's a lot to do with closer by galaxies where we're seeing this difference. And so I don't know if we're particularly close to solving the Hubble tension problem right now. And you might want to ask Chris here on the Space Telescope team to invite some Hubble tension people on there. Maybe they can give a great presentation on, where we are at with that, because that's a little outside of my own. If I were to say things like that,
so maybe we can get him on one day.
Yeah, nasty emails from scientists. I already know that I probably annoyed someone about, why didn't you say my theory about LRDs? They're Martians or whatever.
I do have a couple questions I saved to the end from some JHU students who've been watching us. I'd like to ask before we wrap up.
Mm-hmm.
Sure.
First one, if brown dwarfs don't get their energy from nuclear fusion, how do they generate energy?
They don't generate energy. They are slowly cooling off. They were hot because the gas cloud collapsed, and now they're just slowly cooling off. They're not making new energy or fusing to release light as like a star, but they have the remnant heat from when they were formed. And so this is how we thought up until we realized that was nuclear fusion. We thought was powering the sun. And it's like a classic Astro 101 problem to ask students like, okay, if the sun were powered by the fact that you take a big hot cloud and you collapse it down, how long would it live? And it's much shorter than the lifetime of the actual sun. So something else must be powering it. And so inside of brown dwarfs, it's like, like Jupiter essentially has done the same thing, but Jupiter's smaller. So it's cooled off a lot. It's cooled off for the last like 5 billion years to its present temperature.
Gotcha. Thank you very much. All right. And another question from the same class. Is there a consensus on what are the little red dots besides the ones that are brown dwarfs? It seemed like based on the talk, there were a couple different things.
Yeah, I think that we're really coming to believe that it is a rapid growth of a supermassive black hole. As I said, every galaxy, this one right here, all the galaxies you see probably at their centers have a growing supermassive black hole. It's like a big result from the last 20 years of astronomy that every time we look at galaxies, we see some sort of evidence that there's probably a supermassive black hole growing there. And it's not pulling in the galaxy. The galaxy and it grow in lockstep. The galaxy mostly doesn't feel it. It's just that's where the gravity is. And as it grew, that's just where the black hole fell over time and grew. But those black holes are at a mass where they had to have grown at some point, right? If we know that they have millions to billions of suns worth of stuff inside them to help them get, this big, when did that stuff fall on? And we maybe think that LRDs are probably a mode in the early universe where some of these supermassive black holes grew super fast and they may have been shrouded by gas. So like I'm following what Rohan Naidu was saying, that maybe these things were in a very specific state and they've got a galaxy around them, but we're seeing this really crazy rapid growth rate that we just couldn't have seen with Hubble because we needed a longer wavelength data and they were maybe too faint for us to see them with Spitzer.
That's something we've been talking about in the chat is how can we be sure? And the more precise our instruments get, the more data we have, the more sure we can be about things as we observe.
Exactamundo, yes.
Yeah, 100%. So you may not know the answer to this, but if you don't, what is the furthest or oldest, depending, maybe the same thing, object that we have detected or observed, or alternatively, what's the oldest or furthest object that you have observed?
Yeah, so the farthest galaxy that we've observed and confirmed is MOMZ 14, which was Rohan Naidu, actually. He's on the Miracle. He has this great paper, came out like 2 or 3 weeks ago. It's an unambiguous detection of the galaxy. We have emission lines. Like a number of people that I talked about in this talk also had a hand in doing that. It's an incredible galaxy. The farthest thing that I have found was I found the previous record holder and the one before that. So like I found the first farthest galaxy that was confirmed with JWST as part of the JADES team, and that was a paper written by Brett Robertson and Emma Curtis Lake, who are also part of JADES. This galaxy was JADES GSC 13, and then a year later we broke our own record and JADES GSC 14, and then that stood for like a year, and now it's MOMZ 14. I think probably this fall, with new data, there's going to be another record holder from Caleb Donnan's program that's coming out. There's a lot of galaxies that we think could be farther, but getting spectra is tough. And so like, because these are already very faint and you have to spread that light and it gets even fainter. So we're hoping that we can maybe break the record more, other teams, but like the current record holder farthest galaxy, anything farther than that we've ever found, like and confirmed, comes from the cosmic microwave background. And that was before we had galaxies at all. That was the last time that light, like the first time that light could travel freely. And we, that's like part of the static in old television channels. And that's just like an omnipresent background light from the universe cooling off. But in terms of structures, the current record holder is MOMZ 14, an incredibly cool galaxy that I was really excited to see. Because there's a lot of pressure to have the record. Because you just like wake up and you're like, oh, and like now someone else has that pressure. And I'm hoping that we just get the record broken again and again and again, as it has been over the last 100 years. It's like
you got to get that crown back.
I think that what's cool about science is like going after records is, like that's not why we do science. Yeah. What was nice about GSC 14, this galaxy that was the record holder, was like not that I had the record. It didn't bring me any fame or no one cared. It was exciting. People interviewed me and my grad student, but it didn't. Like it was mostly exciting because like that object's weird. GSC 14 is really bright in the early universe and like really it's extended. Like help challenge theories. Like it's really fun to see the theorists come out and write, this is what's going on in that galaxy. That's why it looks this way. And like I love that while the record is a thing that drives, publications and media, the JADES data, there's someone watching this right now. Maybe it's on YouTube after the fact. Maybe you're in high school and you don't realize that when you get your PhD in a number of years, you'll be using JADES data. These data, we've only touched some small smattering. There's so much science to be done with these and uncover data and like primer data and then, panorama, these other programs. There's so much cool JWST data that we are people limited and not data limited. And with Rubin, we are going to be so people limited. Rubin's going to make a petabyte a night or something like that, terabytes, some insane amount of data, and no human being can go through that. And maybe that's a machine learning problem, but I also think that humans are better at learning right now than machines. And I think that developing new ways of finding these things, that's the future of astronomy. If you are a person who likes a treasure hunt, I will tell you, this is the greatest treasure hunt you could ever go on, because you're learning about not just the history of galaxies, but the reason we look at these things is because these are galaxies putting together the building blocks that are us. At some point, the atoms that are in your body were inside a galaxy in the early universe, put together atom by atom in the centers of stars that lived and died, right? And that's something we can watch. We can watch as the universe gets more and more complicated, as black holes grow, as stars live and die. And we've never been able to do that with the clarity we can do that with JWST. So what a cool telescope. And so exciting.
Nowadays, there are more opportunities than ever to do citizen science because we're going to have such incredible amounts of data. We need all the help we can get. There's no reason you can't be a part of the things that we do.
Yeah. If you've not looked at the Zooniverse, which is a citizen science project, allows you to look at there's Zooniverse people who are already looking at Rubin data. This is something where if you are a person who's like, I really like looking at, I've got free time to look at things, join a citizen science effort, get your name in a paper, and find some weird stuff, right? The universe is so massive. JADES is, again, like a couple grains of sand at the end of your arm in the sky. And we're about to have a movie of the Southern Hemisphere sky. Not at the resolution JWST, but Rubin will give us, over time, we're going to have so much data, and there's going to be so many weirdos. The discovery of brown dwarfs, for some people, was who cares? Why would we care about these brown dwarfs? But for brown dwarf scientists, when I show them this, they're because every other brown dwarf that was ever discovered was in our backyard, essentially. Yes. Because they're very hard to see. They were discovered with a telescope called WISE, that I have a lot of love with, but WISE wasn't nearly as sensitive as JWST or Spitzer. And now we find these brown dwarfs, and we're oh yeah, these are ones in the halo. And they're you have a giant population of halo brown dwarfs. I go, yeah, I got so many that the JADES team doesn't care. They don't know. That's there's no such thing as trash. One man's treasure is another man's treasure is another man's it's all treasure, constant treasure. Yeah. Very cool stuff.
And kind of in between the Rubin's huge swaths of the sky at somewhat lower resolution than Webb has, and Webb, we have the new telescope coming out next year, the Roman Space Telescope.
Roman.
And in fact, we're going to be talking about the Nancy Grace Roman Space Telescope next month. So take this opportunity to advertise that. In July, you can hear about the Nancy Grace Roman Space Telescope and the science program that it's going to be executing. And that's going to be hosted by our colleague Martha Saladino. So please tune in next month to the Deep Space Dialogue then to hear about Nancy Grace Roman.
If you haven't heard about Roman is what if someone just dropped a Hubble in your lap and you could now, with knowing what you know about Hubble, redesign Hubble to do things that Hubble couldn't do, that JWST can't do. It is a great mixture of a JWST. It's like if JWST and Rubin were let's make a third one that kind of combines some of the best traits of both, and they're going to work in tandem. The next several decades of astronomy promise scientifically to be really exciting. There's more complications, but I don't want to get into that. I'm having a great time with you.
It's not going to be a fire hose of data. It's going to be the Niagara Falls of new data. It's just
Niagara Falls isn't even touching it. It's here in Tucson, we get these monsoons where for a second, all the water in the world just falls on Tucson. It's like that. It's just here's a mile of water just falling. It's so exciting. It's so exciting.
Well, I want to thank you, Kevin, for coming and talking with us. Thank you, Grant, for running this platform for us and making sure that everything is working correctly technically and helping us field questions. Mm-hmm. And then our team behind the scenes.
For being awesome and asking all these wonderful questions and being a part of this and following us from the old Hubble channel here. We appreciate each and every one of you. It's because of you we get to keep doing this.
Absolutely.
Yeah, this is so exciting. Like, I appreciate all the people, all the question answers. You had great questions. And like, if you've got more questions for me, like follow me on, you can search me on like Blue Sky or Instagram or whatever and send me messages. Like, I don't get, or just Google me and you'll find my email address. It's very easy to find it. Like, I love answering questions. Maybe I can't give like full deep answers, but I can point you to places where you can find. And like, like if you want to hear more about GST 14, I've got a YouTube channel. You can just search for my name. Just do a Google on the name. You'll find me.
All right. Well, thank you everyone for coming. Thank you for your time, and keep looking up.
Yep.
Okay.
Done.
Okay.
Done.
Great. That was fun.
That was
Great.
great.
Is your dog ready to be a Quattro dog? For full safety information, side effects, and warnings, click Learn More or visit CordeliaQuattroLabel.com. Consult your vet or call 1-888-545-5973.
Charles, welcome back to my office.
Thank you for having me.
The early universe calls.
Yes, it does. In fact, you have a book called The Early Universe on your bookshelf right there, written by Cobb and Turner.
Yeah.
Remember that one?
Yeah.
That was one of the textbooks we all had to read
Early
back in the olden days.
universe.
Yes, that's right.
But that's old enough so that what they were talking about, the early universe, at least in terms of stars and galaxies, we're earlier than that. So back then, I don't remember precisely, it might have been a redshift of 4.5.
That's about right.
And just how far back is that?
That's about 12 and a half, 13 billion years ago. It's a pretty long time. We have now discovered ones at redshift 12.
12.
Okay. Now,
who ordered that?
I know, right? There was just a publication that just happened which cemented for me the reality of this amazing galaxy. So I want to just share that with everybody because it is so interesting. And it brings up questions that we have to talk about, like what really constitutes early universe? What does it mean to be old anymore? The difference between redshift 4.5 and redshift 12 in galaxies time is kind of like 400 million years after the Big Bang compared with, say, 800 million years after the Big Bang. You're basically cutting in half the amount of time you're letting a galaxy grow. And so this object was first discovered using...
It's redshift 12 object.
That's redshift. Object 12 was discovered as a candidate using JWST. It's a pretty long time. We have now discovered ones at redshift 12.
12.
Okay. Now,
who ordered that?
I know, right? There was just a publication that just happened which cemented for me the reality of this amazing galaxy. So I want to just share that with everybody because it is so interesting. And it brings up questions that we have to talk about, like what really constitutes early universe? What does it mean to be old anymore? The difference between redshift 4.5 and redshift 12 in galaxies time is kind of like 400 million.
Sorry about that, guys. I accidentally went to the next thing, but they ended that. And just to give you some information about what I'm going to be doing with some of the channel and stuff, on July 5th and 6th, I will be doing a stream of me doing observations with my telescope and everything. You guys will be able to see directly into the telescope, all of that. It'll be an excellent opportunity for you to see some of the stuff I'm doing. And I plan to be doing these during the entire year, throughout the whole year, of doing a live stream of me doing those observations like that every weekend, as long as the weather permits and as long as I have the time to do it, I'm going to make sure I do it. I'll let you, they'll be posted in my scheduling of everything on YouTube. I'll schedule them out. And if something happens that something can't happen that week, I'll move it to the next week. So just be prepared to jump on there Ask me questions, whatever you want to do. I'll be out there doing it. And you guys will be able to see through the telescope. Everything I get to see, you get to see. And we might expand it to other nights, but we'll see what ends up happening.